Hello, everyone. My name is Alex Matrosov, and today I will be presenting attacking hardware root of trust from the UEFI firmware. And I will be discussing some of the problems when basically the hardware root of trust not really in hardware, and some software take care of it, and it became some of the security problems. So actually, I will skip the intro. So disclaimer, I'm working for NVIDIA, but this talk, it's not for my employer. All opinions is mine, all responsibilities is mine, all the 0 days is mine, and bad jokes too. So, yep. Actually, I switched from easy targets like Gigabyte and Asus, which I presented last year on the OffensiveCon. So I focused on my Lenovo P50, which is more interesting target, and actually not based on American megatrends, which is more fun for me because Phoenix BIOS, I not touch it a lot, and been a lot of surprises for me. So actually, it's agenda for my talk, and we will start from some of the discussion, what is the problem actually overall with the hardware root of trust, and then actually we'll be discuss some interesting stuff, because Lenovo laptops do have like a compute trace, which is kind of anti-theft feature, and they say it's possible to permanently disable in BIOS setup options, but it's not really true. And I will be show you why. And actually, compute trace can be disabled and enabled from the operating system, and it's also quite interesting because basically, even if it's permanently disabled, you can re-enable it. Cool. And I'm doing some firmware research quite a while, and actually SMI handlers, it's kind of like a callback functions from the BIOS to the operating system level. Always been a security concern for me, and actually I discovered some cool stuff which is used on enterprise level laptops for automating some stuff for configuration, even for security too, over Windows management interface, which is cool. You now don't need actually a Ring 0 driver to call a semi-handler. Yep. And it will be some bootguard bypass based, of course, on implementation of Phoenix BIOS, especially for Lenovo, or it's Lenovo engineers make a mistake. I don't know. So, and yep, it's an agenda for my talk. Let's start it. So, hardware root of trust, it's hard because it's actually really hard to support after the vendor bake it in silicon or RTL. So it's can't be updated. And for OEMs, it's very, very hard to support in the field the devices, not only actually x86 devices, any devices. And usually, vendors try to basically make some, I would say not a backdoor, but the way to basically communicate and reconfigure the system, or just basically bypass if something go wrong, this hardware root of trust, and we will see some of the examples today. And also, this kind of things as a hardware root of trust, it's very hard to update, as I mentioned, and actually it's also hard to implement in a secure way, because you have as example, in secure boot, you have a transition states between chain of trust states, and then you need to basically secure transit all the secrets between the stages, and usually performance became its most important than security, and yes, it's some fun stuff there. So in the most of the cases, basically the root of trust, it's mixed between firmware and hardware. It's not always in hardware because it's no way how you can basically put everything in the hardware. And also, most of the cases, it's just like some fuse, which is just a storage, which is locked some of the value inside the hardware, or it can be some specific bit, which is just lock some of the memory region or whatever, make a signal for the firmware to do something specific. And yep, secure state transition is very hard, and we will see. So I will start with some of the picture, because it's always people asking me the question, what is the reason of UEFI firmwares? Because you need a lot of levels of bypass. As example, you need a RC, then privilege escalation, and then you basically can go from the operating system level to firmware. But look on this classification, which I actually released recently in my blog post. So, and it's a lot of stuff can be very, very sensitive, especially for the data centers, for enterprise networks, and other things. And most of the things, as example, configuration, secure configuration, it's even not considered about like security problem. Some of the vendors like Gigabyte, MSI, and Asus Tech even don't sign their updates properly. Actually, this picture also from my blog, from my previous blog post, it's about how many things you need to get in the firmware. Yeah, I will skip it just as a reference. And yep, if you think you have TPM on your platform, yes, you do, but think about physical access for this piece of TCG being not even considered as a threat model, in a threat model. So, and actually, Jeremy Boone been show a lot of issues when they can make man in the middle between TPM and the firmware which is communicating for getting some of the secrets. And other picture, it's actually Tremel Hudson make some fun of it to basically intercepting directly to solder at some wires. And it's a scheme of the bootguard boot flow, which been actually in details discussed last year. I will not go really deep, but thing is, everything is locked. It's a perfect world. We have some root of trust, which is baked in the hardware. We have other things which is have a secure transition way, and yeah, so it's good. Looks good, right? So, but think about, we have a not perfect world, and microcode and ACMs, which is actually stored in a padding, which is highlighted on the picture from UEFI tool, and I released last year update for UEFI tool, which is can parse all the BIOS guard, boot guard information. So, and it's not covered actually with boot guard. You know why? Because you need to execute all this stuff before on initial stage actually of verification, and it can't be covered because who will be basically check all this stuff. And thing is also you can downgrade the microcode and ACMs, at least on my laptop, which I try as a target on this research, which is also fun. My previous year research, I've been talking about bin diffing ACMs, and they do have a lot of stuff. Most of the vulnerabilities which is Intel fixed there, it's not all of them really easy to exploit or really straightforwardly exploitable, but it has some stuff there, and I would suggest to look if you're interested. So, yep. And in this case, we're basically missing two pieces of the root of trust, which is basically not locked and can be downgraded. I would say, of course, you can't really find the issues with microcode. You can, but it's really, really hard. And I didn't see only if you find some of the issues not exactly. Basically, it's baked in microcode, and Intel need to update it, but it's not basically related to bootguard because I didn't see it before, because it's actually just verified the signature for ACM. And actually, ECM is a quite interesting place to look because it's one of the, it's second stage to verify. It's even executed before reset vector. It's one of the points why it's actually not covered by bootguard. Okay, so. Hardware, it's not flexible, it's expensive. OEMs don't like locking secrets there because supply chain is very, very, very difficult for that. The cost for the vulnerabilities is very high, no updates, right? So recalls or something like that. And all the vendors reducing the hardware locked secrets, they try to basically lock in the bits or something like that to make it more simple and mix, mostly it's a mix, hardware plus firmware in common and actual implementations. So let's move a bit to more interesting stuff, which is will be covered, like we learned something about the hardware root of trust, and now we'll see the examples how it can be basically broken. Yeah, how this research gets started, you know, like you can get actually some VMI information over SCPI, which is usually have some like BIOS version, some simple stuff, but someday I get this message when being upgrading my Windows 10, and it was running an action disabling the boot guard. Cool, right? So, but how come? how you basically can disable the boot guard, which is basically have root of trust in the hardware from the operating system level, even if you have administrative privileges. It's kind of concerning me, and I was a bit Googled more about enterprise features of Lenovo laptops, and wow, they do have Windows management interface, basically, which is communicating straightforwardly to the firmware, and it's accessible from the operating system level. How they can change some configurations, how they basically communicate really with the BIOS, it's just a static data, or they really have something which can be really interesting, have a really interesting attack surface. And also, like, we do have access over the network to this interface, of course, because it's enterprise, and you need to basically deliver some changes on the configuration to many machines in your network. And it's actually how many options you have to change over this interface. And yeah, it's like a lot. And I was, okay, what is most interesting for me? And look on it. So you can disable TXT or enable, you can disable or enable BIOS update by end users, you can disable or enable security rollback prevention, downgrade and use 1 days, also cool. But I was thinking it's something else can be there too. So how basically you can extract this information? I've been using just read-write everything, which is not open source, but it's a free tool. I would say the driver is very weird, and I would not suggest to run on your real machines, but yeah, for research, it's cool. And I've been dumping ACPI tables, and this actually is a table, DST, it's the name. You can easy to just grab VMI in the search. You can find a lot of instances, and there's a lot of configuration data, which is can basically just treated by string. And it's like, wow. And Lenovo being very nice, they provided even the Visual Basic script to change a supervisor password from the operating system. And it's not my script, I just downloaded from Lenovo website. So welcome to brave new world. And I was thinking, okay, it's cool, right? So we read the documentation, but what kind of components it can be in actual BIOS, which is basically provides these interfaces. And Lenovo remote configuration update, sounds cool. And also setup automation, setup under operating system also sounds like a good example. But Lenovo setup under operating system SMM sounds more cool, because it's system management mode, and it's kind of really not like more privileged than management interface. I mean, like Intel IMI, but it's interesting in a lot of cases because you can actually, if you escalate the privileges to SMM, you can get access to the physical memory, and it's sensitive for multiple security features on the machine based on the virtualization. So, okay, need to dig into that. And actually, Lenovo setup under OS have like this kind of functionality, and for me, been interesting to look more on actually compute trace disable and enable feature, because I've been reverse engineered compute trace in my previous research back to 2016 when presented on Black Hat Asia rootkits, and actually it's Myth and Realities for UEFI rootkits. Yeah, I already forgot the name of the talk. It was actually very cool stuff there, because we've been reverse engineered with my colleague Eugene Rodionov some of the configuration for compute trace, but like I always been thinking they're using a hardware fuse to basically permanently disabling it, but not true. So they just use really a byte value, but we will discuss a bit later. So Lenovo setup under operating system SMM, they do have 12 SMI handlers, which is basically can be communicated from the Windows management interface to to the BIOS. And what is the interesting thing, you don't need an actual driver, because usually to call SMI handlers, you need a kernel mode privileges to do it, or reading 0. So, and with Windows Management Interface, you just need to have administrator privileges, which is much hidden to basically communicate with if it will be malicious actor inside your BIOS, right? So basically, it's one more thing for forensics people in the room to be considered as attack surface for hidden stuff. And okay, so actually set up automation SMI handlers. So I've been reverse engineered just 4 of them, and but it's really more. So you can see the list. It's a lot of them. So you can just use fuzzer from chipsec, and some of them actually have problems with call-out vulnerabilities, which is nothing user. I think it's a lot of information on public, even on my presentation, how you can exploit it. So I will not go digging into that because, yeah, it's like nothing new. Because basically, developers, I think, just use this old version on new BIOSes and like don't care about updating it. So, yep. And actually, honestly speaking, most of the BIOS vendors, they try to reduce number of SMI handlers in their BIOSes because they try to reduce attack surface because it's like callback functions directly to the operating system, easy to fuzz, easy to attack, and privilege escalation to SMM, it's kind of not a good thing for security. Even if you can't persistently modify spy flash, you can leave some time there and think about the servers, right? So especially for virtualization, you can basically go to privilege escalation to SMM, then do some stuff, and it's quite enough because you can, your shellcode actually will be equal to downtime for the system. Okay, and let's dig more about the compute trace. And looks like compute trace never dies because you can't really disable. So why basically I get interested more in compute trace? Because it's been very good and interesting research from the ESET, and the guys basically find first known in the wild rootkit lowjacks, so it's been cool. And but my talk not about this one. So my talk about the legit rootkit, which is Lenovo Systems has. So, and actually, how many people in the room use Lenovo laptops? But just for research, I hope. So, and think about, here is a list of actually components which is related to directly to Lenovo, not Lenovo, actually, Absolute Software compute trace component. Think is like Lenovo really using the old version of it, and they just reuse on the, even in some of the new laptops. And problem is they not updated. I don't know why, maybe like their license expired for updating from the vendor, and all the old bugs, it's still there, and it's kind of like concerning me to continue using these laptops, but I really like it. The keyboard can survive from without it. Okay, so it's actually why I was sure it's cool stuff for presentation, because I've been tweeting a few weeks ago, and it's like get a lot of attention. Oh, quite cool, so I need to dig more. And it's a slide from my Black Hat Asia 2016 presentation. And here is options from your BIOS setup, specifically on the compute trace screen. And you can see, actually, it is an option to permanent disabling it. And it's not true. So, yep. Let's move. Yeah, it's actually no possible to permanent disable it because it just software baked byte value which is stored in the configuration, which is named very scary as a hidden settings. And so it's just showing some architectural information about compute trace. So we do have some like configurational data in two storages, which is named a security config and hidden setting. So, and actually, CompuTrace have a SMI service broker, which is managing SMI calls between different components, and actually also have some secure way communicating with sensitive components over a mailbox in SMM. But if you reverse engineer the interface, not even the mailbox, how basically you properly communicating with the SMI handlers, you don't even need to deep to mailbox stuff, which is also quite scary because it's really make things easier for the attacker to understand. So it's recovered structure for Lenovo security configs. Actually, a lot of values unknown. You can see last value, it's 80 bytes fields, or I don't know, maybe some of them it's not really bytes, but I don't know what is it. But I recover a lot of interesting stuff which I already discussed, and one of them it's like a secure boot, which is an option in BIOS setup, and it's tied to Lenovo security config, and it's actually can be changed over VMI. But you need a supervisor password, which is also will be discussing a bit later. So, CompuTrace services, it's has, so basically my most interested, it's been SMI handlers table, which is, has a 3 SMI handlers, and it's actually stuff been reverse engineered for Black Hat Asia for my talk, and that time I actually didn't know what exactly SMI handler is doing, and I get more interested actually for this particular research when I discover it's no way how you can permanently disable or enable, right? So actually you have a CompuTrace enable, disable, and you can understand what kind of configuration you currently have to call a CompuTrace state. And also you need to call some of the CompuTrace enable action or disable action from the Windows management interface. Yeah, that's kind of like interesting information to think about. To basically, maybe you need just switch your lovely keyboard from Lenovo laptop to something else. But yeah, let's dig into CompuTrace services. And actually, I've been looking on how basically the flow working, and I was discover interesting value in NVRAM. NVRAM, it's basically a memory which is stores some of the configurational data which is known as a UEFI variables. So, and yeah, you can just dump it with some of the tools like a chipsec, or you just can use a, if you have a driver like read, write everything, you can just browse some of specific memory region to get that. And unfortunately, I just reverse engineered one field, but it's, you can see it's more there. So one field which is basically tied to CompuTrace state. And the other thing, as I already mentioned, it's security config from, also it's a variable, and it's like really a bit field with some of the values which is basically true or false positioned. And also, here is a reconstructed Lenovo security config, which is we already discussed. And all these bit values, it's actually about byte. It's actually 1 byte. It's 1 configuration data, and it has just 1 for to be true. And actually, here is reconstructed flow to reading security config and changing the different states. And it's quite complex, so I will not dig into the assembly because it's no need for that, and it's ugly when I've been reconstructed it. I mean, like, not assembly is ugly, it's just like the tool not providing a really readable code, and even after my try to beautify the code manually, it looks not that good, unfortunately. And yes, I reconstructed, just basically put some most important information and on this pseudocode slide. So basically, it's values which is called to compute trace enable, and then you basically can switch the state between false and true. It's really two ifs and nothing else. So it's checking first compute trace state is supported, then basically change the configuration. But most interesting also, it's SMI compute trace disabled, and compute trace state have actually four values, 3 Boolean values, which is enabled, active, and disabled. So you basically can control the state and understand it's active or not. So, and one of the things which is I've been like, wow, that sounds interesting. It was a disable secret key, because I was discovering, oh, it's sending some byte value, but this value being derived by something bigger for the 4 bytes. And but derivation, it's like symmetric, so you basically don't need to know any secrets. You just need to send the correct byte value. So cool. I not really to dig into that, right? So here is how it's matching the keys, and this key you need to basically permanent disable the compute trace or enable from the operating system. And yeah, so matching the key, it's not a constant time. Cool, right? So we can brute force because it can be called from the operating system level. And I was thinking what kind of fuzzing ideas I can implement. And okay, 1 byte value secret stored in SPI flash in VRAM. And can be different by laptop model. Yes, I have also in my lab T540P, which is have a different value, but problem is like it's kind of old laptop, and P50 it's more interesting because it's have a Skylake, and actually newer line on P has the same problems as mine, and it's ThinkPads. So it's ThinkPads as a mobile workstation, have a like a Xeon CPU on board, so it's quite cool laptop. I was like it, but now just for research. So basically it's small script on Python, like it's pseudocode mostly, to brute force with a chipsec. So you can call SMI handler, you can just brute force this SMI value, because actually they don't have a constant time, so you can even make it brute force even faster than I do, but it was enough because byte value it's not too much too fast. So fast, check, repeat, profit. Disable key is 57 by hex, and actually it was really fast. It's like less than 10 minutes to brute force. And okay, my concerns on compute trace, so it's actually a good idea to have an anti-theft for enterprise, but kind of like it's third-party component, and it's not very well updated by vendor. And it also shows a problem with the supply chain, because basically the vendor, maybe they lose the license, or they not lose, like they just not continue the license, or they just don't want to basically continue, or they just basically support the old version, whatever. So supply chain problem here is pretty clear. And okay, you do have a laptop, but you can't really disable this feature for forever. So, and all these drivers on each boot, it appears. So, and communicating from the operating system level, it's possible, and it's proven. So you can see it works. Just try on this script, and you can brute force your value. So on this disable key value on your Lenovo laptop. So, and yeah, and actually number of SMI handlers, it's huge. So overall, it's more than a 20. And currently modern BIOSes, they try to reduce, actually have a less than 20 inside, like for all the SMI services which communicating from SMM to operating system. And yeah, it's quite dangerous stuff. So, and one more thing, I've been trying to research for this research, and actually it's also interesting, it's embedded controller. And embedded controller historically sits on x86 platform very long time, and usually as a TPM on my first slides, it's not really considered as a security boundary, because basically if you get into that, embedded controller has a DMA access and a lot of other stuff, which can be basically attack other components, and multiple stuff is just not considered from going that way. So, okay, it's basically embedded controller, just dump it from the documentation of my Lenovo P50 vendor. It's basically microchip. So yeah, it's quite good. So, and a lot of stuff there. It even supports the BIOS guard features, and we'll talk a bit about that later. So actually, yeah, it's interesting because embedded controller update tools, it's usually have a separate flow. And how it works, so you run the tool communicate with embedded controller, say, okay, we switch to the update mode. Embedded controller took this update container inside the internal memory and then verifies the update. It's in perfect world. How it works in the real world, so some of the vendors, not microchip actually have a good verification, but some of the vendors just don't verify properly their package for update, and or even don't have zero verification, just calculating the hash as a CRC32, which is not really a hash, right? So checksum for container being properly delivered to the internal memory and just going to update. Okay, and actually, one more thing, I was basically try on this part to deliver one more interesting bug, but it's still under responsible disclosure. I will not drop the name of the vendor, but I can talk about the bug. So, bug is very interesting because what one of the vendors of embedded controller does, so they have a update package and has a signature, like a public key on the end and hash value. Actually, hash value, it's not CRC32, it's SH256, which is good. I mean, wow, that's cool, but let's play with this update. What if we modify the hash? Okay, it's not accepted, it's returned something weird and not go well for update. Okay, they check the hash. Okay, let's modify one bit of update, actually code itself, or package, whatever. So, boom. It's been delivered, but platform actually been not booting. Okay, so it's been a bad idea. But anyway, so on different platform with the same chip, I was, okay, let's actually try to reconstruct the flow, modify the update, but have the same hash. And it was fun, it worked. So problem was, actually, the vendor signs the hash, but don't check the hash versus update itself, which is cool, right? So, okay, yeah, it will be faster, right? So why we need to check the hash? Yeah, so probably I will be drop this in my blog a bit later, but yeah, you know all the details, just I actually keep the vendor name, but yeah. And Intel BootGuard, so actually a cool feature as we discussed, and it's actually, I really like it, so it's changed the rules for implementation of secure boot and actually attack surface a lot, but always it's some things coming from the vendors and actual implementation. So yeah, I've been actually showing some bypasses of the boot guard last year on the OffensiveCon, and oops, I did it again. So yeah, so how actually hardware-based root of trust became a software. So recovery mode is evil. Secure transition of the chain of trust on different stages is hard and slow. So always performance here is quite difficult because think about, so you have a sleep or hibernate when you close your lid from the laptop, you need really fast to blink your screen after you open it because it's marketing feature, right? So, and a lot of vendors basically try to make a transition some of the secrets from the hardware root of trust, not really leaving the hardware root of trust, they just transition the state true or false. As example, chain of trust being verified, all the states being verified correctly before, and then starting from that point. And it's not really secure, and I will show you why. In most of the cases, basically without hardware reset, yeah, it's what I just discussed, it's really a pure software. Performance reasons. Enterprise hardware need remote update tools, right? So also a lot of things landing there. Nobody use Intel BIOS Guard, which is like, okay, BIOS Guard, it's different from boot guard. It's armoring the update process to lock in inside the hardware, but how many vendors really use it? So I would say not a lot at all, because I just found a few of them. We'll be not doing marketing, but yeah. So one more stuff, it's a recovery, and actually it's from Intel NUC, and they flash in a recovery block firmware, and it's cool, right? So, and it was just a specific value which is showing the state inside the pay driver, and in the specific value actually which is demonstrated, which I discussed before. So yeah, we do have this verification result there. And this bug was found by embedded guys, and yeah, it's very cool. So I really enjoyed this stuff, and it was pointing me to different direction from American Megatrend BIOS to the Phoenix. It's different bug, but it's also like a byte value. I will show you after that. So yeah, so the stored value verification result, it is ignored, and starting recovery actually without any verification of it. Which is cool. So here is a bug. Yeah, they make some credits on my blog post because it's pointing to them to some of the directions of this research, and actually their research pointing in another way to actually in the Phoenix BIOS to find this stuff. So yep, bootguard P. So look on the Zero Nights presentation this year. Very cool stuff. Really like it, and also make me more concerning about the bootguard security. But actually, how bootguard bypass usually works. So you need screwed up the hardware component because you can't really change it if it's actually burned in the fuse. So if fuse burned, yes. About not burned fuses, it's been discussed in my previous year presentation. So I will not go this loop because I have just a bit of time and want to discuss more stuff. So yeah, you remember the screen, right? And actually, Lenovo have a platform configuration data init, which is Lenovo PCD init driver inside BIOS. And this I've been looking on it because platform configuration data, it's always cool. And I've been just like brute forcing different values to understand what they're doing. So, and I said, okay, set PCD 6 to 0 or 1, depending on byte as on this specific physical memory address. So, okay, that's kind of like interesting. And it's a UEFI tool. I just open the padding file, and it's, of course, not covered by bootguard. And you can actually change one byte value, which is highlighted on the screen. And I will share some details on my blog post in my blog after, so just to the people more understand details to reproduce the stuff. And I think it's kind of like a manufacturing mod or something else when you need to disable the boot guard to recover the system or basically make some pre-productional things. Oh, actually, I forgot to mention, Lenovo security config also can make a CPU debug enable from the operating system level for x86 platforms, especially on Intel. Okay, so if you change this value and reboot your system 3 times, so I really didn't know on the beginning this amount of tries. I just brute forced it because, oh, it's not working. Let's try again. Let's try again. And it's suddenly been working after 3 tries. So, and actually, more on that. Lenovo security config has the value which is being a 3. And I've been, okay, it's a number of tries. That's why it's working after the 3 times. And it's been, I suppose it's been a manufacturing mode or something like that, tied to that. But what is the security concern here? Think about, so first of all, if you really think your secure boot is secure and have a hardware root of trust, not. It is a marketing proposal, but if you think on the real implementation, it can't be not truth. So don't trust the vendors, always check. So the usability in enterprise world, in many cases, the main enemy of security. So also, a lot of times, security features, especially on boot flow, can be wrong after updates. And I mean BIOS updates. And for recovery that, people leave in the backdoors, just basically when people start, oh, I have a warranty, extended warranty, whatever, so trying to communicate with the vendor, and of course vendor don't want to lose the money, so they try to leave some of the byte values, whatever, for basically do some stuff to recover your laptop. And they really frequently don't consider reverse engineering in their threat models. And software engineers, not security engineers, software engineers, always think to recover the stuff, it's really difficult. And with the modern tools especially, it's not actually that difficult. And also for many people, it's fun, and they just will be doing it for free time, as I do. And also, the vendors understand permanent disabling option differently. So, because think about, as example, reading about that, in the BIOS settings, I was thinking about compute trace, it will be disabled forever. So it will be no way how it can be re-enabled, right? But it can be. And yeah, it's make some concern about security of the firmware. So one of the options for some of the Lenovo laptops, it's flash their core boot, but if you're not really firmware professional, don't do that because it will be even weaker than just use the default firmware. Because it's a lot of configuration. If you just flash it with the default configurations or use some open sourced BIOSes, leave it on internet, you really don't know what is there. So yeah, it's not a good idea. When hardware-based root of trust transfers the states, so software takes care of it, and it's not hardware anymore. So basically, think about, so it's no way how you can always have secrets. Like, you can have a keys inside hardware, but also if the key leaves the hardware, it's not in the hardware locked anymore. So, yep. And I think that's it. So thank you very much for your attention. But I expect some questions. We have a bit of time. Thank you very much.
Questions? Thank you
Yes,
very
please.
much. Okay. Test? Oh, thank you very much. I have a question. Have you tried to get, for example, something like core boot running on your device when boot guard is disabled?
Excuse me, you say core boot
Yes.
running on your device if the boot guard is disabled?
Yes.
Yes, you can. But if it's enabled, I would say, basically, if you can't disable and firmware basically will be always try to verify the chain of trust from this point, so your platform will be not boot. So yeah, it's really case by case. If you show me the laptop, I will tell you more. And yeah, let me just update the firmware there.
That was an awesome talk.
Thanks, Bruce.
Yeah.
It's pleasure to get this feedback from you.
Yeah. So for the CompuTrace thing, instead, like, would Lenovo take some feedback from you where, like, for example, instead of just turning off a bit, they just like disable in the
so you call the SMI handler,
yeah,
and in the EIX register you have like a 1.
Yeah, exactly.
Yeah.
But couldn't they just like make it so that like they just like remove the piece of code that injects the WPBT table so that like CompuTrace would never ever be like, I mean, like literally like the binary would not even be there anymore. I mean, would they do something like that so that you can add? That's like, I mean, that would be a real removal, right? Not just like switching on some bits.
They not really do that. So.
I see. Okay, so
Yeah.
we're screwed. Okay. So, yeah, and the next one, I guess, like to control, like having a WMI driver to control, like via ACPI to control BIOS.
So basically, how it works, you have a Windows management interface, which is operating with ACPI. So you basically just modify specific data in the specific table in ACPI, and then some like SMI driver or like BIOS, let's say BIOS SMM driver, try to read this value in the loop. If it's get modified, so something change it in the configuration data. It's how it works.
Okay, cool. But like when you make these...
Oh, sorry. No, not like that. It's about the different stuff. It's about remote config. About, particularly about the CompuTrace, you need to modify a CPI value, which is basically will be flag VMI SMI call. Then you basically go there.
Yeah. And then, like, when you install CompuTrace, do they? I mean, like, they actually load a driver, no? Like, when you download this, when you actually deploy the software.
Yeah.
Like, they actually load a driver, like.
On the operating system, and they use HTTP in this old version. Why I say they even not patch old bugs because it's known for years.
Yeah.
It's
Cool. All right. Awesome. Thank you.
Yeah, let's make Raphael to answer. Question.
And thank you for the talk. I have a question regarding the WMI interface. It seems like it's sometimes you need to supply the supervisor password to access some of the features.
You're right. SVP password. You need. Oh, sorry.
So I'm not really sure I've understood. Like the CompuTrace interface, you can reach directly without the supervisor password, or do you need the password to reach WMI anyway?
It's interesting. I will tell you why. If you not support, like set up your supervisor password, they transfer from the operating system, from ACPI, the value in the specific register, it's not supported. So you can change it, then it basically will not ask you supervisor password. But it's hard to brute force because they track number of tries, yes.
Okay.
Yeah, so if you set up the supervisor password and you didn't know about this trick, and actually I not dropped this stuff because, yeah, Lenovo asked it not doing that. So,
okay, thank you.
More questions? Always at the opposite side of the room.
But yeah, it's actually a really complex attack surface there because I would say they a bit overwhelmed the stuff inside the BIOS because it's like a lot of double checks, but in the same way that not really sync it. So if you basically bypass one, it will be no apply like to all of them, but you bypass the piece of trust.
I have a question for the CompuTrace feature. Does it mean when it's being disabled permanently that I could reflash or reset the firmware so that it would reappear afterwards?
Yes. First of all, if you make it a physical reflash, so it still have some hidden SPI flash storage or like to have some bits. So Lenovo security config have some specific related stuff to that. So basically, they try to recover these permanent disabled features as a bitmap from this hidden storage. If you modify it there and flash, so yeah, you're done.
Do you have like a list of affected systems?
I will share it in blog post, yeah. So
Thank you very
some
much.
things I can't today because of the restrictions for responsible disclosure stuff.
Someone at the other side of the room? Okay, I have a question left. I didn't really get the whole part about the very interesting integrity checking of the update. Did they really just check the signature of the hash, but
You
not
mean embedded
recompute
controller,
the
right?
hash?
So what they did, so they basically have a, they signed the hash, but they not verify the hash versus update. Yes.
Just check the signature of the
yes,
hash.
exactly. So I would say
Genius.
maybe somebody forget to add the code, or it's basically for performance, I don't know. Chip is quite like simple, and it's like even not ARM, so it's slow.
And in this case, did you name and shame them, or is it still not?
I can't. So
Okay, not yet.
don't want to be fired.
You can even
But
have a microphone
maybe
for
if
that.
you provide me some shots of whiskey, I will reconsider that.
Hey, one last question on this topic. Did you actually try to flip bits like in different places of the firmware?
No. Specifically, I found this platform configuration data storage. So you can clearly see it's a lot of zeros, and just few of them basically have a data in it. So I checked the different storage on the separate laptop, and I see, oh, it's a different value, and okay, it's something can be changed there, and also they have different bytes set it up. So and I played, yeah, I basically tried
one possibility, one possibility is maybe they check certain part but not other parts, and you just found a part.
That I don't know.
Okay.
So it
So that
works
was
to
the question.
disable the boot guard,
Yeah.
but maybe it's work for disabling something else. That I don't know. You're right. So it can be more, but I still think each byte value is just for one feature, but it can be a bitmap. Yeah.
Hello. Hello. Thank you for the talk. One question. How did you trace the actual value that the UEFI is actually using? Did you do that from the operating system level?
I download update for my laptop from the vendor website. So I use the UEFI tool to open it and see what kind of the Dixie driver does. What else? So and also, so Nikolai Schley developed the perfect tool for the forensics and also for the reverse engineering UEFI firmware. My update being just for the boot guard. All other stuff, it's on him, so he basically main contributor long time ago. So, and it show you like the drivers you can extract it and open an IDE Pro because it's x86 based. So yeah, just go on it. But honestly, reverse engineering the UEFI drivers inside the IDE Pro, it's kind of tough because if you don't recover some of the internal structures, so it will be like very, very difficult to read code. So even if you know assembly pretty well and did a lot of area before. Yeah.
Okay, then that was it.
Thank you very much.
Let's have a round of applause.